Hi students, welcome back to second lecture on isomerism. Now already we know that in the last class we discussed about chain isomerism, positional isomerism, ring chain isomerism, metamerism and functional isomerism. Okay. Next another important structural isomerism today we are discussing, that is tautomerism. Really among the different types of structural isomers, tautomerism is very important. Definitely high weightage should be given to tautomerism compared to other structural isomers. Okay, right. So tautomerism is a very interesting concept, and here to understand the tautomerism, first I am going to give very fundamental example by using C3H6O. This is my molecular formula, C3H6O. Okay, by using that molecular formula, otherwise if you are going to test chemical test for C3H6O, for example, actually we don't know what about the structures present according to that molecular formula. Just you go for chemical test. Now this molecule giving positive test for ketone, that is giving positive test for ketone, that is also giving positive test for alcohol. So way of approach is very important in case of tautomerism, right? First I am taking one molecular formula C3H6O, right? And if you are taking chemical test for that molecule, that is giving positive test for ketone and positive test for alcohol. Okay, so according to these chemical tests, now how we are going to write the structures of these two compounds. Now first one I am writing like this: CH3, C double bond O, CH3, ketone, and that is also giving positive test for alcohol. That's why you can write like this OH. These are the two possible structures. Okay, for example, if you are taking first compound, this one giving positive test for ketone, and this one giving positive test for alcohol, Okay, so how we understand in the conversion, interconversion of these two molecules, and finally how we are giving definition for tautomerism, right? Now in these two molecules, ketone and alcohol, or sometimes this is also known as enol. First one is keto form and second one is enol form. So these two are what exchanging together, keto to enol form and enol to keto form, right? So if you want to give definition for keto enol tautomerism, once again I am going to take same keto form here, keto, and what is our enol form? This is our enol form. Okay, very interesting concept, right? Keto form and enol form. So how we are converting that keto form into enol form? For example, if you want to convert keto form into enol form, first we are going to ask hydrogen atom. Just you ask one question to hydrogen atom. Yes, so where are you from? Okay, now in the first molecule ketone, here how many hydrogen atoms present? Yes, there are 3 hydrogen atoms. We know that carbonyl carbon adjacent carbon atom is designated as alpha carbon atom. Right side we have one alpha carbon atom, left side also one alpha carbon atom, right? Now in case of enol form, here how many hydrogen atoms present? Yes, there are 2 hydrogen atoms. In keto form, how many alpha hydrogen atoms present? 3 alpha hydrogen atoms are there. But in this enol form, on the same carbon atom, now here on the same carbon atom, how many hydrogen atoms present? 2 hydrogen atoms are there. So if you are asking hydrogen atom, now it will say that yes, previously I was at carbon atom, I am coming from carbon, finally I am coming to oxygen atom. Okay, now just I am giving numbering like this: first carbon, second carbon and third oxygen atom. Okay, just you observe these two molecules. First, in between these two, 1 and 2 carbon atoms, there is no pi bond, and between 2 and 3 atoms there is a pi bond. But here between 1, 2 and 3, between 1 and 2 there is an extra pi bond. Next, between 2 and 3 there is no pi bond. So pi bond is disappearing between 2 and 3. New pi bond is formed between 1 and 2. Okay. So now here how we are producing or how we are converting this keto form into enol form. So to convert keto form into enol form, so we are transferring proton from first carbon to third oxygen atom. Okay, so how we are representing? Now sigma bonding electrons are moving like this and shifting of pi bonding electrons. Okay, pi electrons are shifting from carbon to oxygen atom, and sigma bonding electrons are migrating like this. Then finally you are getting this enol form. Okay. So how we are producing these two molecules? By the movement or oscillation of hydrogen atom. So in the first molecule, hydrogen is present at first carbon atom. In the second molecule, same hydrogen shifting to oxygen atom. Okay, there is a oscillation of hydrogen. There is a oscillation of proton. Okay, because of oscillation of that proton, now we are getting that keto, enol, again enol to ketone, keto to enol, enol to ketone, like that. Okay, this is what we call keto enol tautomerism, right? So we can write the definition like this. You write same point. Structural isomers produced by the oscillation of hydrogen from 1 to 3 and 3 to 1. 1 to 3 and 3 to 1. Structural isomers produced by the oscillation of hydrogen from 1 to 3 and 3 to 1 are known as tautomers. Okay, and phenomena is known as tautomerism. Okay, that is the fundamental definition for tautomerism. So what we are giving here, structural isomers produced by the oscillation of hydrogen atom. Why? Because only hydrogen atom is oscillating from 1 to 3, 3 to 1, 1 to 3, 3 to 1, like that. Okay, structural isomers produced by the oscillation of hydrogen from 1 to 3 and 3 to 1 are known as tautomers. And what is the phenomena? Tautomerism. Okay, that is the fundamental definition, right? Clear? Next one, what are the different types of tautomerism that we will discuss here? Different types of tautomerism. First case, diode system. Okay, what is the diode system? To understand diode system, here I am taking one example, HC triple bond N. Nitrogen fifth group element, it has one lone pair of electron, right? HC triple bond N. Now this nitrogen lone pair receiving proton from carbon atom. Let it is first atom and carbon second atom, right? After shifting of proton, finally hydrogen connected to nitrogen atom. Because of providing lone pair of electrons, what is the charge given to nitrogen? Positive charge. And here these sigma bonding electrons are leaving behind carbon atom. Now here we are giving negative charge after removal of proton. Okay, now these two are in equilibrium. Now you observe there is a oscillation of hydrogen atom. Oscillation of hydrogen atom from 2 to 1. Again, if you want to get the same thing, now again you transfer proton from 1 to 2. Okay, whenever there is a oscillation of hydrogen atom from 1 to 2 and 2 to 1, that kind of system is taken as what? Diode system. You can write same point, movement of hydrogen from 1 to 2 and 2 to 1. Movement of hydrogen from 1 to 2 and 2 to 1 produces diode system. Movement of hydrogen from 1 to 2 and 2 to 1 produces diode system. This is a very good example. Now you can take one more example also by using HNO2 nitrous acid, right? HN double bond O. Here I am giving lone pair of electrons. Okay, now this lone pair of electrons receiving proton from that oxygen atom, let it is first and this one second, right? Here after shifting of protons, so what we are writing? Double bond here hydrogen atom. Next one, oxygen with negative charge and nitrogen atom with positive charge. Okay. And sometimes we can also write like this, by the replacement of positive and negative charge, NH double bond O, next one coordinate covalent bond. So in place of positive and negative, here positive charge is present on more electronegative atom or less electronegative atom. Here your positive charge is present on less electronegative atom, and a negative charge is present on more electronegative atom. So by the replacement of positive and negative charge, we can introduce coordinate covalent bond. So both structures are same, no problem. Okay. Now these are the very good examples for diode system. So what is the meaning of diode system? Your proton is oscillating from 1 to 2 and 2 to 1. Right. Second system, triad system. Here I am taking triad system. Triad system. Triad system nothing but 1-3 position, right? Very good example. Same previous example. C double bond O H I am taking. Okay. And here I am taking first 2 and 3. 1, 2, 3 atoms. Now here I am shifting sigma bonding electrons and pi bonding electrons. So this oxygen atom is receiving proton. It produces enol form OH. Okay. 1, 2, 3. Again, if you want to get same keto form, so how we are transferring hydrogen? 3 to 1. You are getting this one. Again from 1 to 3 you are getting enol form. So what happens in triad system? In triad system, movement of hydrogen takes place. Movement of hydrogen takes place from 1 to 3 and 3 to 1. Movement of hydrogen or oscillation of hydrogen takes place from 1 to 3 and 3 to 1. Okay, that is the triad system. There are a lot of examples for triad system. Not only keto-enol tautomerism, we can use imine and enamine system, nitro and acinitro systems, nitroso and oxime systems, that we will discuss at the end of the tautomerism. Here these two examples are enough. Triad system, keto to enol form. In triad system, movement of hydrogen takes place from 1 to 3 and 3 to 1. Is it clear? Fine. For example, sometimes you can see this molecule, 6-membered ring system, right? Double bond, here double bond O. Here initially how many hydrogen atoms present? Yes, there are 2 hydrogen atoms, right? And you can see this molecule also, OH, okay? Where from this hydrogen atom coming? Here at this carbon atom, previously there was no double bond, only 2 hydrogen atoms are there. Now here, after shifting of hydrogen atom from carbon to oxygen, we are getting this molecule. Again, these two are in equilibrium, right? I am not going to write the equilibrium constant value. Just you observe the transfer of proton or movement of proton, right? Here, this is not the 1-2 system. That is not the diode system. Simply I am writing diode and triad systems. Is it a diode system? This is not the diode system, and this is not the triad system. This is not the triad system. Okay. Whenever there is an oscillation of hydrogen other than diode system and triad system, that should be taken as what? Space tautomerism. Space tautomerism. Very important example, space tautomerism. This molecule not coming under diode system and not coming under triad system, and this one is taken as what? Space tautomerism. Very good example and very, very important. Okay, right. These are the 3 different types of tautomerism: diode system, triad system, and space tautomerism. Now, next one, what is the condition for tautomerism? Once again, yeah. Condition for tautomerism. Condition for tautomerism. Condition for tautomerism. Here I am taking some examples like this. C double bond O. This is the unsaturated system, and your double bond is present between 2 different electronegative atoms. Now, which is more electronegative atom here? Oxygen atom. Oxygen is more electronegative than carbon, and at alpha position I am taking hydrogen. This is our alpha carbon atom. Okay. Now this hydrogen atom is acidic hydrogen or not? Yes, this is acidic hydrogen. That is the requirement condition for tautomerism. There should be presence of acidic hydrogen atom, right? First molecule. Here you can take aldehyde and even sometimes ketones, right? General representation. Here alpha carbon atom, it contains alpha hydrogen. Yes, this molecule can also shows tautomerism. Not only these aldehydes and ketones, we can write like this C double bond N and carbon with hydrogen atom. In amine system, it is considered as alpha hydrogen. This one also shows tautomerism. And even in case of our nitro compounds, N double bond O oxygen. Here on carbon atom, I am taking alpha hydrogen. This molecule also shows tautomerism, right? And nitroso compound, here hydrogen, this molecule also shows tautomerism. What is the important condition? There should be presence of acidic hydrogen. Actually, instead of alpha hydrogen atom, we better to say that acidic hydrogen atom, right? In all these cases, there is a presence of acidic hydrogen and these molecules shows that tautomerism. For example, if molecule is given like this, now C double bond O, here I am taking hydrogen, molecule is given like this. Is it possible to produce tautomerism? Yes. Why? Because here this is the alpha carbon atom and this one beta carbon atom. For example, if you remove proton from this carbon atom, so what is the result here? C double bond O, next one double bond, and this carbon atom getting what? Negative charge after removal of proton. Then after that we are looking for resonance. After formation of this carbon ion, there is a conjugation negative sigma pi sigma pi. So there is a conjugation. Conjugation is present or resonance is present, right? Because of the presence of conjugation or resonance, this carbon ion is stable or unstable? Yes, this is the stable, and because of that reason, that hydrogen atom is taken as acidic hydrogen. Okay, this molecule also shows tautomerism. So what is the main important condition for tautomerism? For tautomerism, molecule should contain acidic hydrogen. And second important point, that acidic hydrogen should be present on sp3 carbon atom. That is the condition. If it is present on sp2 carbon atom, we are not using for tautomerism. What is the condition? That hydrogen should be present on sp3 carbon atom, right? For tautomerism, molecule should contain acidic hydrogen and that acidic hydrogen should be present on sp3 carbon atom. Right? Okay. Now you write first question here. Which of the following molecules can show tautomerism? That is the question. Which of the following molecules can show tautomerism? Yeah. Write that question. Which of the following molecules can show tautomerism? Here I am giving some examples. From that you try to identify which molecule can exhibit tautomerism. Aldehyde, ketone, and here another ketone like this. Yeah. any type of example they can give. Yes. Yeah, these are the molecules. From these molecules, identify which molecule can exhibit tautomerism, right? So whenever molecules are given, first what we are searching? We are searching for acidic hydrogen atom, right? Here carbon, adjacent carbon atom is alpha carbon atom, there is a hydrogen. Actually here 3 hydrogen atoms are there, right? That means what is the important condition? At least one acidic hydrogen should be present in the given molecule, right? So this molecule containing acidic hydrogen, that shows tautomerism. First one. Second one, yeah, left and right hand side it has acidic hydrogen atoms. This molecule can show tautomerism. Next, come to third molecule. Here left side and right side hydrogen atoms are there, right? Hydrogen and hydrogen, hydrogen and hydrogen. Yes, acidic hydrogen atoms are present that can exhibit tautomerism. Now here come to this example. Yes, left side 2 hydrogen atoms are there, right side 1 acidic hydrogen atom is present. That molecule also shows tautomerism. And come to this example. Yeah, here. Yes, left side there is a hydrogen, right side also acidic hydrogen atom is available. That molecule shows tautomerism. Next one, no alpha hydrogen, no tautomerism. From right side there is no hydrogen. Why? Because here that hydrogen atom is present on sp2 carbon atom. We are not using that hydrogen. Okay. Left side here 2 hydrogen atoms are there. From left side we can use for tautomerism. That molecule also shows tautomerism, right? Here no chance. Why? Because there is no alpha hydrogen atom. Alpha hydrogen or acidic hydrogen atom. Okay. So but every time we cannot expect that hydrogen atom from alpha position, but we require acidic hydrogen atom. Now come to this example. Yes, here acidic hydrogen atom is present. It can exhibit tautomerism. Only simple thing, just to remove the proton and just verify resonance is present or absent. So automatically you will get the idea. For example, if I am taking a negative charge, negative sigma pi, there is a resonance or conjugation. So because of the presence of conjugation, that carbon ion is stabilized by resonance and this proton is taken as acidic proton. Yeah, in this molecule, right side 2 hydrogen atoms are there, left side also 2 hydrogen atoms are there. This molecule shows tautomerism. And here from left side we have 1 hydrogen, from right side we have 2 hydrogen atoms S. It can exhibit tautomerism, right? And in this molecule, from left side 1 hydrogen, right side 1 hydrogen. Here from right side 2 hydrogen atoms are there, but in the last molecule there is no hydrogen. There is no acidic hydrogen atom, and that molecule not exhibits tautomerism. Yes. Come to next example. Yes. By using what 6-member ring system, here I am taking 2 carbonyls like this, C double bond O and C double bond O, 1-2 position, and even sometimes they are giving 1-3 position and 1-4 position also, right? C double bond O and C double bond O. Okay. Next one we can write like this, double bond O and double bond O, triketone, right? And next important example, here double bond, here C double bond O, 1 double bond I am taking inside the ring system, right? And here C double bond O. For example, if molecule is given like this, by keeping 2 double bonds inside the ring system and they are changing position of double bonds like this. Next one, another important example, double bond O, again double bond O. Next one, they can give like this, double bond O, carbonyls at 1-2 position, right? And for example, they are giving like this, C double bond O, here methyl and methyl. Next one, double bond O, here methyl and methyl, and outside the ring system here methyl group is given. Write down these examples. Yeah. Come to first one. tautomerism possible or not in the first molecule, right? Now in this molecule, carbonyl adjacent carbon atom, yes, hydrogen and hydrogen. Here hydrogen and hydrogen. There is no extended conjugation, just we are looking for alpha hydrogen atoms, acidic hydrogen atoms. Yes, this molecule can exhibit tautomerism, right? Come to this one, we have a lot of hydrogen atoms from this carbon, hydrogen, hydrogen. From here, hydrogen, hydrogen, yes, hydrogen and hydrogen, yes. It can show tautomerism. Next one here, hydrogen, hydrogen. From alpha position, 2 hydrogen atoms are there. Hydrogen, hydrogen. At least one hydrogen atom is sufficient to exhibit tautomerism, right? Come to next important example, hydrogen, hydrogen. Yes, it has 2 hydrogen atoms. It has 2 hydrogen atoms. Yes, it can exhibit tautomerism. Now you can select hydrogen atoms from this carbon atom and as well as from this carbon atom. Because of extended conjugation, this molecule also shows tautomerism. And what about this example? Yes, it has alpha hydrogen atoms, acidic hydrogen atoms. Here also acidic hydrogen atoms. It can exhibit tautomerism. But actually sometimes here what is happening? Now pi bond migration takes place for getting what? Higher stability, right? After pi bond migration, now this is the compound. Here we are using hydrogen atoms from these carbon atoms, right? So finally that molecule can exhibit tautomerism. Come to this example. Yes, we have alpha hydrogen atoms, acidic hydrogen atoms. Your molecule can exhibit tautomerism. And here we can select hydrogen atoms from this carbon atom. Already we know that this is an example for space tautomerism. Here also same thing, here space tautomerism. Yeah. Now you observe this example, very important. There is no acidic hydrogen on sp3 carbon atom, there is no tautomerism, right? And come to this example, no acidic hydrogen, no tautomerism. Here also same thing, at this carbon atom, no hydrogen, no tautomerism. And come to this example, here we have one acidic hydrogen atom. For example, if you generate carbanion here and looking for resonance, negative sigma pi, yes. This molecule can exhibit tautomerism. All these are very, very important examples, right? For example, if they are giving a compound like this 1,2 diketone, yeah, this one 1,2 diketone or 1,3 diketone, and sometimes they are connecting aromatic ring systems like this, double bond O and C double bond O something, okay? And even sometimes they are giving esters also, double bond O, C double bond O something, okay? One part is ketone, another part is what? Ester. Now sometimes they are giving these bridged compounds. These are very, very important. Here they are giving carbonyl functional group. And even sometimes they are changing position of that carbonyl like this, C double bond O. And one more simple example, yeah, C double bond O, methyl and methyl. These are very, very important examples. Very important. This one also very important. Yeah. Come to first example. Yes, it has acidic hydrogen atoms. Here also same thing, acidic hydrogen atoms. This molecule can exhibit tautomerism. Next one, we have hydrogens from middle carbon atom, and acidic hydrogens are available from left and right side carbon atoms. But in general, if you want to write tautomerism, we better to select these protons. Reason we will see later. Yes, this molecule can show tautomerism. Here at this carbon atom we have availability of 2 hydrogen. Yes, this molecule also shows tautomerism. Come to this example, hydrogen and hydrogen. Here also 3 acidic hydrogen atoms are available. Yeah. Now this is very important example. So before going to this example, so we need one important concept, that is what Brett's rule. You remember this point, according to Brett's rule, for example, if there is a double bond at a bridgehead carbon atom. First, what is the name of this carbon atom? This carbon atom is known as bridged carbon atom. Bridged carbon atom. And what is the name of this carbon atom? Bridgehead carbon. Bridgehead carbon. Yes. Bridgehead carbon. Okay. So now at a bridgehead carbon atom, what is hybridization of this carbon? sp2 hybridization. What is the required bond angle for sp2 hybridization? 120 degrees. Okay. But actually there is no 120 degrees bond angle. Because of absence of 120 degrees bond angle, this compound is expected to be highly unstable. Highly unstable according to Brett's rule. Okay. According to Brett's rule. Very, very important. According to Brett's rule, first condition, at a bridgehead carbon atom, sp2 carbon atom is present, that molecule is highly unstable. What is the reason behind it? sp2 carbon requires what? 120 degrees bond angle. But actually there is no 120 degrees bond angle. So because of that reason, your molecule is highly unstable. Now according to Brett's rule, one more example here. If same bridged compound is given and here positive charge is present. Actually this Brett's rule is concept of general organic chemistry. There once again we will discuss, no problem. But here to explain about the tautomerism, minimum I require these two molecules. That's why I am taking that Brett's rule. Here sp2 carbon atom is present. What is the location of your sp2 carbon atom? Bridgehead position. So here that carbon atom is sp2 carbon atom. Okay. So once sp2 carbon atom is present at bridgehead position, again same thing. What is the required bond angle? 120 degrees. But actually there is no 120 degrees bond angle. Now this carbocation is also highly unstable because of absence of required bond angle. Almost these molecules are said to be hypothetical molecules because of highly unstable nature. So finally, just to remember these 2 points. First point, according to Brett's rule, now this double bond, once sp2 carbon atom is present at bridgehead carbon atom, now this molecule is stable or unstable. This is highly unstable compound. And next one, same at bridgehead carbon atom. So if positive charge is present at a bridgehead carbon atom, positive charge is present. Okay. Again, this is highly unstable species. Highly unstable. Remember these 2 points. Both requires 120 degrees bond angle, but unfortunately there is no 120 degrees bond angle, and these two are what said to be highly unstable. Again coming back to what same question, you look at this one. For this carbonyl, it has alpha hydrogen, but what is the problem? If you are using alpha hydrogen atom, you can develop a double bond between these two carbon atoms. For example, after removal of this is our molecule C double bond O. Okay, C double bond O. For example, if you remove proton from that carbon atom, then how to develop enol form? This is our enol form. Yeah, O minus, here we are keeping pi 1. Is it stable or unstable? It is highly unstable. Why? Because here what is the carbon atom? sp2 carbon atom. What is the required bond angle for sp2 carbon atom? 120 degrees bond angle. That's why, because of absence of 120 degrees bond angle, this is highly unstable. Very important example, highly unstable. Again coming back to same question, once acidic hydrogen atom is present on bridgehead carbon atom, in tautomerism we are not using that hydrogen atom. Okay, right. Here it has 2 options, hydrogen from bridgehead carbon atom, hydrogen from this carbon atom. There is no chance to use hydrogen from bridgehead position, but we can use these two hydrogen atoms, this molecule can exhibit tautomerism. Very important. We are not using this hydrogen atom. We can use these two hydrogen atoms for tautomerism. Okay, right. Here, yes, there is a hydrogen atom at a bridgehead position, but we are not using that hydrogen atom. Next one here at alpha position, there is no hydrogen, acidic hydrogen, so no tautomerism. Okay, these are the examples. Next one, in case of keto enol tautomerism, you remember these points. So before going to write keto and enol forms, in keto enol tautomerism, for example, left side there is a keto form and right side enol form. Okay, keto and enol form. So how to represent that equilibrium constant? Equilibrium constant equals to concentration of enol form by concentration of keto form. So you write down this one. In that equilibrium constant equals to concentration of enol form by concentration of keto form. Okay, right. Now here three cases are there. For example, at equilibrium, concentration of enol is greater than concentration of keto, right? And concentration of keto approximately equals to concentration of enol form. Here, concentration of keto is less than concentration of enol form. Yes, I think first and last condition same. I am writing 1 second. Yeah, keto is greater than enol form. Yes, these are the three conditions. For example, enol concentration is greater than keto form, then what is the equilibrium constant value? That should be greater than 1. Clear? Second case here, equilibrium constant value approximately equals to 1. Third case, if keto form is more than enol form, equilibrium constant value less than 1. These are the three important conditions. They are asking question now on equilibrium constant value. Equilibrium constant is decided by stability of keto form and enol form. For example, stability of enol is more than keto, then automatically concentration of enol form is more than keto form. Then what is the equilibrium constant value? Greater than 1. For example, approximately these two are what? Equal stability, then equilibrium constant equals to 1. For example, keto form is more stable when compared to enol form, then what is the equilibrium constant value? Less than 1. Okay, now these are the three conditions. Let me come to first example. In keto enol tautomerism, for example, here CH3 C double bond O CH3 given. What is the name of this form? Keto form. And how to write enol form of this compound? So very easy to write. This is the enol form of our compound. Yes, enol form. Okay. So first one here, there is no aromaticity, there is no hydrogen bond strength, nothing is there. Only simple ketone and enol forms are there. In that case, according to the bond strength here, keto form is more dominating when compared to enol form. According to bond strength criteria, here equilibrium constant value can be expressed as concentration of enol by concentration of keto form. Concentration of enol by concentration of keto. So in that case, what is the equilibrium constant value? Less than 1. Why? Because here keto form is more when compared to enol form. You are getting equilibrium constant value less than 1. Whenever simple ketones and enols are what given, your equilibrium constant value is less than 1, especially in case of what acyclic systems, right? Now come to next example. Here C double bond O 6-member ring system, and what is the enol form of this molecule? Yes, this is our enol form. So left side this one keto form and right side enol form. Okay, right. Here also same thing, keto form is more when compared to enol form. There is no additional features of enol form, no hydrogen bond, no aromaticity, no extended conjugation like that. So in that case, just we are giving high priority for bond strength. Ketone bond strength is more when compared to this one here. What is the equilibrium constant value? Okay, less than 1. Yes. Next example. So this type of molecule is given C double bond O. What is enol form of this molecule? This is the enol form of given molecule OH. Yes. Now this is the keto form and this one enol form. Yeah. Keto and enol form. Right. So which is dominating here on the basis of our aromaticity. So product concentration is more when compared to reactant concentration. What is the additional advantage of this molecule? Enol molecule has aromaticity, right? That aromaticity is stabilizing factor or destabilizing factor? Definitely stabilizing factor. Because of that aromaticity, enol content is more when compared to what keto form. So here equilibrium constant equals to concentration of enol by concentration of keto. So what we are getting? Equilibrium constant value less than 1 or greater than 1? Yes, greater than 1. Very important example. So now here we can write one point that if aromaticity is present in enol form, then enol form is stable than keto form. Here aromaticity is the stabilizing factor. Okay, right. Aromaticity is present, then enol form is stable than keto form. We are getting equilibrium constant value greater than 1. Yes, come to next example. I am giving example for space tautomerism. Yes, here double bond C double bond O and H and H. Okay, now this is our enol on the basis of our space tautomerism. Here this molecule is aromatic compound or non-aromatic compound. This molecule is non-aromatic compound. And this one is aromatic compound. At equilibrium, definitely enol content is more compared to what keto form. Then what is the equilibrium constant value? Greater than 1. Very important example. Equilibrium constant value should be greater than 1. Okay, right. One more important example. Here molecule is given like this: double bond O, again double bond O. 3 ketones are there, and corresponding enol form is like this. This is our enol form: OH, again OH. Left side, what is the nature of this compound? Non-aromatic compound, right? And right side molecule, this one aromatic compound. Yeah, aromatic compound. So definitely aromaticity is the driving force. Now this equilibrium is more observed towards right side when compared to left side. And what is the equilibrium constant value? Greater than 1. Very important example. So aromaticity is the driving force. On the basis of what aromaticity, right side compound is more stable when compared to what left side compound. And what is the equilibrium constant value? Equilibrium constant value is greater than 1. Yes. Next one, for example, 1,2 diketones are what given like this. 1,2 diketones. What about content, enol content and ketone content? Now in this example, there is a delta plus and delta minus. Why? Because between carbon and oxygen, which is more electronegative, oxygen is more electronegative when compared to carbon. That's why we are giving partial positive charge and partial negative charge. Okay. Yes, this molecule is suffering from dipole repulsions. This one suffering from dipole dipole repulsions. Dipole repulsions are stabilizing factor or destabilizing factor. Due to the presence of dipole repulsions, your molecule is unstable. Your molecule is unstable. Okay, but how we are stabilizing that compound? Here two options are there. Now we can apply CC bond rotation. There is a chance for CC bond rotation. After CC bond rotation, your molecule orientation is like this. So once one carbonyl upward and one carbonyl downward, simply your molecule is escaping from dipole repulsions. And what is the second possibility? You can write enol form. So like this, okay? So actually experimental studies tells that compared to this enol form, now this ketone form is what? More stable because of the bond strength. Now in that case, we are not giving priority for enol form, okay? Very important. Now ketone form is more better than enol form. So in that case, what is the equilibrium constant value? Less than 1. Yeah. Come to next example. If same compound is given like this, double bond O and double bond O, 1,2-diketone. But here, this is not the acyclic compound. This is the cyclic compound. In cyclic compound, CC bond rotation restricted. There is no chance for CC bond rotation. Okay. This molecule also suffering from dipole repulsion, delta minus and delta minus. Your molecule is expected to be unstable. But how we are stabilizing that molecule? Yes, we can stabilize by applying tautomerism like this, OH and C double bond O. After writing the enol form, just you verify what are the possible advantages. First advantage, after writing enol form, there is a conjugation pi sigma pi. This molecule getting extended conjugation or this molecule getting conjugation. And what is second one? There is a chance for hydrogen bond. Okay. Now intramolecular hydrogen bond. Because of these two reasons, now your molecule is what? Highly stable compared to what? Keto form. There is a conjugation and intramolecular hydrogen bond and absence of dipole repulsions. Absence of dipole repulsions. These are the advantages. Because of these advantages, enol form is more when compared to keto form. And what is the equilibrium constant value in that case? Equilibrium constant value is greater than 1. Okay, right. So these are the examples for tautomerism, and some more concepts are there, and we need to discuss about 1,3 dicarbonyl compounds and what are the effects, factors affecting tautomerism, right? And what is the deuterium exchange, kinetic isotopic effect, that we will discuss in the next class. Okay, right.